Okay, let's take a look at the lesson 8 and 9 problem sets today. Lesson 8 and 9, they're very similar lessons. They're all about using certain properties of numbers to help us add and subtract rational numbers more quickly and accurately. So number 1 says represent each sum as a single rational number. A sum really is just a number. When you're looking at a sum, a bunch of numbers being added up, it's just another way of representing the final answer, if you want to say that, the number that you get when you add them all up. So to express a sum as a single rational number means to just do the addition, get the final answer, the sum, and show me express that sum in that way, just that one number. So this says negative 14 plus negative 8/9. Well, in this lesson, we learned that mixed numbers are sums. And so what that means is mixed numbers can be broken up into two parts, their integer or whole number part and their fractional part. And also, if you have an integer, a whole number, and a fraction that's less than 1, usually, if you want to do this properly, then you can combine those two things or add them as a sum and get a mixed number from those two addends. And that's what we have here. They've given us two addends. They want us to represent this sum as a single mixed number. So we have negative 14 plus negative 8/9. That's negative 14 and 8/9. And so if you think about it on a number line, if you were at negative 14 and then you went 8/9 to the left from there because you're adding a negative, you would wind up at negative 14 and 8/9. So 7 plus 1/9, that's the same as 7 and 1/9. So this is just basic practice on seeing a whole number or an integer plus some other fractional part that's usually less than 1, and just combining them into a mixed number. But just being careful with the signs, because when the signs are mixed, if you had a negative integer and a positive fraction, or a positive integer and a negative fraction, then things get really tricky there. They actually didn't give you one like that here. So this says negative 3 plus negative 1/6, so that would be negative 3 and 1/6. And so what happens when you have one that, let's say you had positive 3 plus negative 1/6, these are a little bit harder to combine because you can't just make it into 3 and 1/6, right? You're at 3 on the number line, and then you have to move 1/6 to the left. So this would actually be 2 and 5/6. Okay, so those are much tougher. You have to think about directions on the number line, subtracting the fractional part from 1. Some people like to think of this as I did it as 2 plus 6/6, right? This is the 3. 2 plus 6/6, that's equal to the 3. And then added negative 1/6 to that. And that's how I could get, 2, then I have 6/6, but I add 1 negative 6, so that leaves me with 2 and 5/6. So those are a little bit harder, but they didn't give us any like that, but I wanted to show you. Okay, so the next part says, rewrite each of the following to show that the opposite of a sum is the sum of its opposites. So what this means is that when you have a sum, like let's say 7 plus 1/9, well, that sum is equal to 7 and 1/9. The opposite of that would be negative 7 and 1/9. And you could also get negative 7 and 1/9 by taking the opposite of each addend or each piece of this sum. So negative 7 plus negative 1/9 would get you negative 7 and 1/9. So if you know a sum, or you can express a sum somehow, taking the opposite of that whole sum is equivalent to taking the opposite of each individual part of the sum or each addend, and then summing those up or adding those up. You should get the same answer either way. And so this example too is there to show us exactly that. They have the opposite of a sum, so this is the sum of 9 plus 8, and then since that whole thing is in parentheses and there's an opposite or negative sign operating on the outside, this is the opposite of this entire sum. And so you take the sum first, you get 9 plus 8, which is 17. But then the last thing you do is take the opposite of that, because the negative sign's on the outside of the parentheses. And you get negative 17. Well, they want you to see that that's equivalent to had you just taken the opposite of the 9 and the opposite of the 8, and then added those two things together. So that's what they did here. Negative 9 plus negative 8 equals negative 17. So our job on each one of the next ones is to find the sum inside the parentheses, then take the opposite of that. That's called the opposite of a sum. But then rewrite the expression equivalently as the sum of the opposites. So that's when you take the opposite of each addend or each piece of the sum and then add them up and show that you get the same number either way. So 6 plus 1/4 is 6 1/4. But then I take the opposite of that last and I get negative 6 1/4. And now to write this equivalently as the sum of opposites, I get negative 1/4, because I'm taking the opposite of the first addend, and then I add that to negative 6, the opposite of the second addend, and negative 6 plus negative 1/4 is negative 6 1/4. That's equivalent to what we had before. Now, the next one says the sum is 10 plus negative 1/6, and we're taking the opposite of that sum. So 10 plus negative 6, I think I said 1/6 a moment ago. 10 plus negative 6 is 4, but then the opposite of that is negative 4. Now let's rewrite this as the sum of its opposites. So we had a positive 10, the opposite is negative 10. And we're going to add that to, well, we used to have negative 6, so the opposite of that is positive 6. Negative 10 plus 6 is negative 4, the same thing we got the other way. So the opposite of a sum is equal to the sum of the opposites. That's the whole moral of that story there. All right, let's move on and do a couple of these word problems below. See if I can move the paper up a bit. Number 6 says, Megan said the opposite of the sum of negative 12 and 4 is 8. Do you agree? Why or why not? Okay, so she wants the opposite of the sum of negative 12 and 4. So I just wrote the sum, but in parentheses, so that I could write the opposite on the outside. This is the opposite of the sum. And so I'm going to do it just like I just did the previous questions. I'll add the stuff up in the parentheses first, keep my opposite or negative sign here. And so negative 12 plus 4 is negative 8. And so what we've written here is the opposite of negative 8. Well, that's positive 8. So some people like to think about the negatives cancel each other out. I like to think of it as I'm at negative 8 on the number line, and then I want the opposite of that, or the additive inverses of that, and so I'm jumping way over to positive 8 on the number line. And so I will write, yes, I agree. And it says why or why not. Well, I think showing this expression and working it out from here to positive 8 is enough to satisfy the why or why not part. Okay. Number 7 says, Jolene lost her wallet at the mall. It had $10 in it. When she got home, her brother felt sorry for her and gave her $5.75. Represent this situation with an expression involving rational numbers. What is the overall change in the amount of money Jolene has? So I normally like to work in fractions, but because this is a money question, I'll leave it in decimals, because that's how we talk about money in real life. We say $5.75, not $5 3/4 or whatever. But you could totally do this with fractions if you like. There's nothing wrong with that. So the first thing she did is she lost her wallet. So I think I'll represent that as a change of negative 10 to her money. A loss and negative are sort of the same in my mind. But then she gains $5.75 when her brother gives her that money. And so we need to figure out where we are on the number line now. If we're at negative 10 and we move to the right 5.75, and we can use the skills from this lesson to break that $5.75 or 5.75 into an integer part and a decimal part, just like we did with the mixed numbers with the integer and the fraction, you can do the same thing with integers and decimals. And people do this because it sort of makes it easier to keep track of where you need to go on the number line. So if we're at -10 and we add +5, that puts us at -5, and we still need to add the 0.75. And so if I'm at -5 on a number line and I'm going 0.75 to the right or 3/4 to the right, then I know I'm still going to be negative. I'm definitely not going to make it all the way to 0, but I'm going to be closer to 0 because I'm moving to the right. So 4.25 or $4.25. The common mistake that students make is when they don't break this up into two parts, 5 and 0.75, is they will add the $5 to the -10 and get -5, but then for whatever reason they'll move back to the left for the 7.5. And a very common mistake answer I would get on this question is -5.75 instead of -4.25. And so I'll write a little conclusion that says she lost $4.75. What you don't want to do is write she lost -$4.75. The word lost sort of implies or takes care of the negative part of the number for you. If you wrote lost negative money, then first of all, nobody speaks that way, but second of all, that would be sort of a double negative, and it would sort of imply positive. It would almost be like she gained $4.75. So you could either say the change in her money was -$4.75 or that she lost $4.75, but don't use a word that implies negativity and a negative sign at the same time. I'm going to leave number 8 to you to do without my help. So let's look at number 9. It says a number added to its opposite, which is the same as an additive inverse, equals 0. What do you suppose is true about a sum added to its opposite? Use the following examples to reach a conclusion. Well, a sum is really just a number. Like this 3 plus 4, that is 7. I mean, we know that when we add them up, we get 7, but in its essence, it actually is the number 7, just expressed differently, expressed as a sum. So really the rules don't change here at all. Since sums are just numbers, and we know that when you have a number and you add it to its opposite or its additive inverse, you get 0, then it's going to be the same. Sums added to their additive inverses or to their opposites are also 0. So really all you have to do is show that all of these equal 0, and there's lots of different ways you could do it. So I'll do the first one. This is number A, or letter A, whatever. It says 3 plus 4 quantity plus quantity -3 plus I don't really like how they wrote that without the parentheses between the plus and the negative sign. Okay, so you could do this a couple different ways. You could start getting rid of parentheses. You could use a commutative property to put the 3 and the -3 next to each other and show that those make 0. I think that'd be kind of a cool, interesting way to do it, but honestly the faster, easier way is to just do the math inside the parentheses. 3 plus 4 is 7, and I'm going to add that too, so I'm looking at this plus sign here because I kind of satisfied these parentheses. -3 plus -4, that's -7. The only reason I wrote these parentheses is to separate this plus sign and this negative sign, and we know that 7 and plus -7 makes 0. So that's really the job on each one of these, is to show that, you know, if you have a sum and then you have another sum and the opposites, the sums are opposites, or all of the addends being added in each sum are opposites to the ones from the other sum. That was probably confusing, but I think you know what I'm trying to say. Then you're just going to wind up back at 0. I'll do B. I'll do B the other way. So -8 plus 1 quantity plus quantity 8 plus -1. So the addends of this sum are the opposites of the addends of this sum. So since each of the terms in this expression, or each of the addends, are just being added, and we know that the commutative and associative properties of addition allow us to move things around, really these parentheses aren't actually doing anything. So I'm just going to rewrite it without them. Now if we had a number up against these parentheses that was multiplying into them, or if we had some subtraction somewhere in this expression, then it'd be really dangerous to just take the parentheses away. In fact, you'd almost certainly get something wrong. But since the only things that's happening here is just straight addition, then I know I can do this. And now I'm going to use the commutative property to commute this 1 and this 8. And so I get -8 plus 8 plus 1 plus -1. And now I'll use the associative property to say, well, I'm allowed to add these two and add these two and then add the results or the sums of those at the end. And so, well, these two right here, this -8 and this +8, they make 0. And then I'll carry this plus sign down. And this 1 and this -1, well, they also make 0. So I get 0 plus 0, which equals 0. So the main question here is, what do you suppose is true about a sum added to its opposite? Well, I mean, just by definition, an opposite is a number that when added to the first number in question, you get 0. So I mean, they're almost kind of telling you the answer just by using that word. But you know, the final conclusion to be made from here is that yes, a sum plus the opposite of that sum will get you 0, just like if you had single number expressions. All right, I'll leave that last one for you to do. Let's look at the problem set from lesson 9 real quick. I'm just going to do question 5 really thoroughly for you. If I assigned you 1 through 4, I'd like you to just do them similarly to how you've seen me do question 5. Probably going to want to use a separate piece of paper because there's not really enough room on this sheet. So it says, explain step by step how to arrive at a single rational number to represent the following expression. Show both a written explanation and the related math for each step. So what I'm going to do is I'm going to break this apart slowly, step by step, and add it step by step. And at each step, I'm just going to name the property or the skill or the fact that I used to justify each step. Okay, so I'm going to rewrite this as 1 plus -3/4 plus -12 and 1/4. I literally only made one change there, and that's subtraction is the same as adding the additive inverse. So that's what I'm going to write here to justify that step. Subtraction is adding you're supposed to say additive inverse, but I like to shorten it to subtraction is adding the inverse. So the only change I made, I rewrote this whole thing, except for instead of -3/4, I wrote plus -3/4. Now, this might feel like a lot of, we're going to rewrite this expression several times, looking at each thing that justifies our move each time. It's going to feel like a lot of rewriting. This is very thorough. Mathematicians do this sometimes when they're trying to break things down in like a teaching mode, or if they're trying to prove something that's sort of confusing. I'm going to move over here more on the paper so I can use some of this space over here later. So I'll rewrite this again, and this time I'll write 1 plus -3/4 plus -12 plus -1/4. And so the change that I made that time is that I broke -12 and 1/4 into its two parts, -12 and -1/4. And that's because we learned this fact: mixed numbers are sums. Okay, so next I'm going to use the commutative property. I see that, like, I would rather add the integers together and add the fractional parts together separately. That's easier to me. So if I commute this -3/4 and this -12, that allows me to do that. So I'm going to do 1 plus -12 plus -3/4 plus -1/4. And so I used the commutative property of addition to allow me to do that. So we could live in a universe where you're not allowed to just switch the numbers when you're adding them. Like, what if you got different answers? And so some very thorough mathematicians at some point went back and wrote and proved that you can always do this. You can always switch these numbers, and we're relying on their proof to be able to say, yep, I know I can do that because it's this rule. Okay, so now I want to add the integers, and 1 plus negative 12 is negative 11, and I'm going to add the fractional parts. I have negative 3/4 plus negative 1/4. Remember that trick. If two numbers are negative and you're adding them, you can just add them as if they were positive and then put a negative sign in front. And so 3/4 plus 1/4 is 4/4, which is 1, but they're both negative, so this is going to be negative 1. And now, because I added two numbers over here on this side of the expression and added two numbers over here on this side of the expression, I grouped them the way that I wanted to. It was convenient for me. And you could also say I associated the numbers the way I wanted to, and so that's the associative property of addition. And then the last step would just be to add these two, negative 11 plus negative 1. I'll add them as if they're positive. I get 12, but since they're both negative, I put a negative sign in front. I'm not really sure what step we could claim justifies that last step. We just did it. So here's what mathematicians will often do. This isn't really appropriate here. This isn't really how this is usually used, but when they solve a proof, or when they're finished writing a proof, they'll put a little box at the end to show that they're complete. And when they if the proof is original, like no one else has ever done it before, they'll color in the box. If you have Miss Zavala as your math teacher next year, you might notice that she has this box tattooed on her arm. Interesting fact. All right, I think that's it. If I assigned any of these to you, please do them similarly to this on a separate paper, because you see that there's not enough room there.